Okay, so what we're going to be talking about in this lesson is just a tiny tweak to the formula that we started using in class yesterday. So what we're going to have to learn to deal with is situations where there's not necessarily a one-to-one relationship between the rate and the time. And I'll show you what I mean by that with this first example. So here we've got Craig, and he has some pet rabbits, and they are growing in number by 41%. All right, so before today, what we would have done is we would have set this up so that the number of rabbits he has over the course of time would be however many he has now, and then we would go 1 plus 0.41 to the t power, and that's because we're going to measure the amount of rabbits that there are after t months goes by. But the situation here says that the 41% is kicking in every 4 months. It's not kicking in every month. And then the question goes on to say, how many rabbits did he have 10 years ago? So we've got a crazy situation here where time is measured in years, but the rate isn't occurring every year, which is what we were dealing with yesterday. Yesterday, if I gave you a question that said, how many rabbits did he have 10 years ago, the rate would have said it increases by 41% every year. But now it's every 4 months. So we have to think about what that means in terms of our time. Let's think about a year, start to finish, January to January. All right, so 1 year goes by, and Craig's pet rabbits grow 41% every 4 months. So we've got a 41% that kicks in here, and then another 41% that kicks in here, and then another 41%, right? So this rate happens 3 times in 1 year. So that's how we have to think of this, right? The rate happens in 4 months, 4 months again, and 4 months again, and there you go. So the way we want to look at this is that 41% just occurred or just affected the number of rabbits 3 times per year. So actually, when we set this up, what we're going to do is we're going to have this be 3t, because the time isn't just the number of years. What we're really measuring with our time is how many times the rate kicked in. And since time is in years, it's going to be 3 times however many years go by. So let's set this thing up. How many rabbits did he have 10 years ago if he has 13 rabbits now? Well, we know that right now he's got 13 rabbits. That's going to be our total amount. We don't know how many he had initially, but we do know that the rate is 41%, and we will go with 3t for the amount of time. And since we know what t is, we can call t 10. All right, now we can finally do this. The next step here, we'll just write this as p times 1.41 to the 30th power. And to get p alone, what I'm going to have to do is divide by 1.41 to the 30th on both sides. It's going to allow these to cancel. So in the end, I should have p equals, and I'm going to round to 2 decimal places, 1.65. We know that doesn't make sense, though, right? Because you can't have 0.65 of a rabbit unless it's dead. There's a lot of dispute on how to round a situation like this. Some people would say, well, if you have 1.65 rabbits, then we'll just have to call that one rabbit because that extra can't count. Other people would say, well, what you're doing here is you're trying to get to the closest whole number, so you should just round. What we're going to do is we're just going to round to the nearest whole number because it's a rabbit. So Craig had 2 rabbits. Okay, so let's find a way to deal with this formulaically. We're going to adjust our formula here, so adjusted formula. It's almost exactly like the one we used yesterday, and we're going to keep using it in the future. 1 plus or minus r. But this time, t has to be affected by how often that rate is being applied per unit of time. So what we're going to do is we're going to divide t by n. And I'm going to explain what n is here in just a second. So In this new formula, n is just represented by how often the rate is applied per unit of time. Okay, so within the context of that last problem, our n actually was 1/3. And just to show you what I mean by that, what we did is we did t divided by, and if we want the number of how often the rate is applied per unit of time, in our case, it was 1/3 here, because the rate is being applied every 1/3 of a year. They told us to measure in years, and since it's happening in 4 months, which is 1/3 of a year, then our n would be 1/3. And we know that, just from dealing with fractions and denominators, you could just do t times the reciprocal, which would be 3t. So that's really why we ended up with this 3t here. If we want to stay consistent with our formula, what we're going to say is we're just going to have n be how often the rate is applied per unit of time, and we'll be able to adjust all of our scenarios from this point on. So just a small change to our formula now. If time isn't in a one-to-one relationship with the rate, then we're going to use n to cut up our time. So the money in a bank account is decreasing exponentially at a rate of 5% every 3 years. And that's important because that 5% isn't happening every year, it's happening every 3 years. That's the difference between what we're doing now and what we did yesterday. How many years will it take for the $3,982 that is currently in the account to become $2,000? So we're going to start off with our formula. We're going to have our total amount. We're going to have a principal amount. The money in the bank is decreasing, so it's going to be 1 minus whatever our rate is to the t over n power. So we can start plugging in the values. We know that now the bank account has $2,000 in it because it's been decreasing. It initially had $3,982 in it, and the rate of decrease was 5%. We don't know the time, but we do know that this rate is only kicking in every 3 years. So I could kind of draw this same picture like I did earlier. Here's a year, 1 year. The rate never kicks in, not then. We have to go a whole nother year. And even still, our money has not decreased yet at that 5% rate. 1 year, 2 years. It's not until we do a third year from January to January that finally we lose that 5%. Right? So this is different than the last one. In the last problem, we were cutting up each year into thirds, and so we were able to just multiply our time by 3. But this time it's the opposite. This time we have to wait 3 years for this rate to happen. So because we're waiting 3 years, we have to take our time and divide it by 3 to figure out how many times that rate actually kicked in. At this point, it's just algebra. We're just solving these functions just like we have been for the past 2 weeks. We're going to divide both sides here by 3,982. Okay, simplify my fraction on the left-hand side. Now the question I'm really asking here is what power of 0.95 equals 1,000 over 1991? So I could write that as a logarithm. Log base 0.95 of 1,000 over 1991 equals t over 3. And I'm almost done. Got to get rid of that 3. So I'm going to multiply both sides by 3. So in my calculator, I can use the log base function and calculate 3 times log base 0.95 of 1,000 over 1991, and that will give me the time. The time should come out to 40.28. And you might say, okay, we got to call it 40. We do not, right? Because you can have part of a year, so we can leave that as a decimal. So we're going to say 40.28 years. All right, if you wanted to get really specific, you could figure out what 0.28 of a year is. It'd be 40 years and like 100 days or something. So you could figure out what that would be. All right? So really the only change between what we did yesterday and what we're doing now is we're just going to be changing t a little bit because we're going to have situations where there is not a one-to-one relationship between the rate and the time.